Not to be outdone, the New South Wales University of Technology, now known as the University of New South Wales, commissioned the computer called UTECOM, University of Technology Electronic Computer. They received a large grant from the state government to study nuclear power, and an electronic computer was considered to be essential to that task. State government policy at the time meant that they were going to be buying a British machine, and the options were a Ferranti Mark I, a Lyons Leo Mark I, or an English Electric DEUCE. The DEUCE was an improved version of the Pilot Ace, which British computing pioneer and codebreaker Alan Turing had contributed very significantly to, and the DEUCE was what was ultimately chosen by Professor Rex Vowels in 1955. UTECOM was operational by September 1956, but sadly broken up for scrap in December 1966.
My father was Rex Vowels. He was responsible for ordering the machine. He appointed Ron Smart. Ron Smart went off to England for about 6 months prior to the arrival of UTECOM.
The future director of UTECOM, Ron Smart, was sent over to England in July 1955 to undergo the maintenance and even the programming courses of the machine as it was being built in England. When the DEUCE computer was ordered in 1955, it was stipulated that a name panel be attached to it with the word UTECOM on it, which stood for University of Technology Electronic Computer. Ron Smart and probably Les Hill and Brian McHugh, the senior programming types, were already planning and running lectures to staff and possibly later year students.
Back in 1957, I started working on UTECOM at the University of New South Wales. It was the second computer in Sydney at the time, after SILLIAC at Sydney University.
Well, when I arrived at UTECOM in 1960, there were two engineers, Robert Reid and Rodney Bell. Now, Rodney had only been there for about 1 year, whereas Robert Reid started it back in about 1957. So he's been there most of the time that UTECOM's been running.
It was my computer from 7:30 a.m. to 9:30 for 4 years, and I'd hand it over.
I started at the University of New South Wales in 1961 as programmer and was put in charge of the maintenance of the machine for at least 2 years.
An engineer's life consisted of arriving by 7 every morning to turn the machine on. In later years, it ran 24 hours. In those early years, it was turned on at 7 a.m.
UTECOM had 1,350 vacuum tubes. It ran with a clock frequency of 1 megahertz. I could walk inside it standing upright. So it was over 6 feet tall, about 8 or 9 feet long, and there were 4 bays of modules. The tubes themselves were inside the computer, and on the outside, as you open the doors, was all the wiring and the resistors and capacitors and things, and that's where, of course, I would connect my test equipment. It worked on lethal voltages, and in the 4 years I worked there, I can remember it belted me twice.
My role at UTECOM initially was to write programs, I guess, but I had to learn the basic machine code.
You programmed in binary. You programmed it in ones and zeros.
UTECOM used a 32-bit binary number, had 12 delay lines, had 32 words in each of them, and the 32 words followed one another serially through the machine in time.
It's not decimal, it's binary. You don't get the ones and the tens and the hundreds, you get the ones and the twos and the fours and the eights, and they're coming up out of the mercury delay lines.
The memory there was a rotating drum, and the memory and data were stored as charges on that rotating drum.
UTECOM had one input device and one output device. The input device was a card reader.
These were standard 80-column cards used in industry since the turn of the century, when they were used for the American census, for example.
UTECOM came with a set of subroutines, and the subroutines were in the form of drawers and drawers of punched cards. We'd have little filing cabinets of drawers, and we'd pull them out, and we'd want to take matrix multiplication out, and we'd search through and we'd find the particular card stack that did a matrix multiplication. We'd feed that into the computer.
It had 2 video display screens. You could see a matrix of 32 by 32 dots in which messages could be displayed. You could see numbers, you could see words, and the demonstrations programs were available where you could see results in the video monitors.
There was a program called Worms, where 2 worms would move. If they met, 4 worms would diverge, and if they met, 8 worms, and so forth. They also had on that same CRT display, a dancing hula hula maiden.
Graphics could be displayed using some programs that were available in the library, but you could also do the displays yourself just by punching the holes in the cards in an image that you wanted to see on the screen. So if you were producing a hula girl dancing on the screen, you just punched a whole lot of cards, each one a little bit different from the previous one, with the skirt as she moved around on the screen, so that when viewed in quick succession it looked like a movie. Another one, which was, I think, written locally, was the story of Hickory Dickory Dock. The mouse ran up the clock, and they had a mouse running up a clock. The clock struck 1. Well, it didn't have a gong to sound, it was a buzzer. The clock struck 1, the mouse wrote down. Yes, these were displayed in words on the screen, and these were punched on cards, like Walt Disney might produce Fantasia by drawing on a piece of celluloid an image.
And one of the games it would play was NIM.
UTECOM could play noughts and crosses. I'm not sure who wrote this program, or whether it came from English Electric or whether it was local. But yes, I played noughts and crosses from time to time, and it was used as a demonstration program. You couldn't win.
And I was introduced to UTECOM as a trainee programmer in 1960. I was actually just a few months into my first year of a Bachelor of Science degree, but they were losing so many staff from the UTECOM laboratory, as it was known, that they wanted to see whether someone young with a few brains might be able to pick up what people regarded as a rather complicated machine, UTECOM, or the DEUCE computer. Essentially had me installed as a trainee programmer. They got me to give up full-time study and become a part-time student, and spent all my daylight hours at UTECOM on how to program that machine, particularly so that I could help staff and senior students who would need help compiling programs.
I tried to write a square root routine. Square roots, you need floating point, and this computer only had integers. So I was trying to get the integers in one 32-bit unit and a binary point, and then the fraction in the second. I tried for about 6 months and couldn't get it working. And I decided I didn't ever want to program. I love programming now, but on a first-generation computer, it wasn't fun.
Well, at UTECOM, there were some languages. One of the most important ones locally was George, Charlie Hamblin's development of reverse Polish notation and the use of the stack in simplifying programming. When they held that conference at Salisbury back in '57, Charlie Hamblin presented that dissertation on reverse Polish notation and stack.
For the computer conference, Charles Hamblin had developed and got working his translator, which he called George, for a new programming language using a concept that nobody had met before, which was called reverse Polish notation. Hamblin had noticed that a notation developed by Lukasiewicz back in the 1920s. In that language, you could write an algebraic expression without the need for parentheses. In that notation, the operators preceded the operand. So if you wanted to add A and B, you didn't write A plus B, you wrote plus AB. But Hamblin noticed that you could also write it AB plus, with the operator following the operands. And so his concept was that these operands could specify an algebraic form of language, and this would be translated by his system into an internal form using a stack. As the names were introduced, like A and B, the values associated with them would be placed on the top of a stack. And so A would be pushed onto the stack, B would then be pushed onto the top of the stack, pushing down the one underneath. And then if you wanted to do addition, all you needed to do was to retrieve these top two things from the stack, do the calculation, and put the result back on the stack, so that it could then be put back into the memory of the machine or used in a subsequent calculation.
So because George was a fairly fully functional language, you never had to go back writing anything in machine language.
George was originally written as a compiler or as an interpreter. It was available only on cards because that was the only input medium for UTECOM at the time. We sent copies of George to English Electric. They never published it. They considered it to be slow, that it was not seen as an efficient implementation of the language. And yet it was approximately 10 to 100 times faster than the only language that English Electric had at the time, which was alpha code. George was a deck of cards which took 2 minutes to read in. Alpha code was a tray of 2,000 cards, and it took between 30 minutes and 90 minutes to compile and run. George read in the program, compiled the program, and executed all in a matter of 2 or 3 minutes. Charles Hamblin had an outstanding mind to be able to devise this scheme effectively prior to the arrival of the computer, UTECOM, to have gotten this scheme working in such a short time. Hamblin's work has to have been the world first. In Australian computing, he was outstanding. I don't think he's been subsequently given the credit to which he should be accorded.
If the machine failed, the first thing I would do is open the back door and go inside, close the door, and as soon as I'd close the door, the lights would go off and I'd be in the dark.
We often had to replace a particular kind of capacitor, which exploded, and with a brilliant flash, and you went inside, switched out the lights, and turned the power on and watched to see where the flash came from.
But the vacuum tubes were like the night sky. They'd glow in the dark, basically. And if there was a section in the dark, I would know that I don't have power to the vacuum tubes in that bank. And that, of course, was the easiest fault to fix.
But we didn't seem to have much valve trouble.
A lot of people will say, well, a valve machine wouldn't run for more than a day without a breakdown. Well, that's nonsense.
The fact was that even though we turned the high tension to the machine off every night when we went home, the heaters of the valves were kept on. And that seemed to be one of the biggest problems that overseas organisations had.
They typically had a life of something like 40,000 hours. So you needed a lot of hours to run up before a valve might give up the ghost. It should have been air conditioned. It wasn't. Over a period of a couple of years, the reliability of the machine was reduced. There were components called AOT, which meant adjust on test. And this wasn't an invitation to make changes to the particular component. Consequently, there were changes made to circuits of the machine to correct faults. Instead of finding the faults, they changed these things marked AOT. As the course instructor told us, changing an AOT was putting on a fault to clear a fault, and then there were 2 faults to fix. And so that's what was happening in DEUCE or UTECOM. Over a period of a year or more, there'd be dozens of faults still dormant in the machine waiting to be fixed. By 1962, things were in a really bad way, and it became even worse the following year, where everything seemed to break down at once, like the card reader, the card punch, various circuits. These all needed major repairs. When these units were restored, we had a working, reliable machine. UTECOM, I suspect many of the other DEUCE computers had an amplifier and a loudspeaker that could play sounds, digital type sounds, but it could also play music. First hear the sound of the fans cooling UTECOM. We now hear a George program cards being read in. Now we hear it being compiled. It's through the amplifier, which is the speaker, so yes, except for the noise of the fans or the air blowing through the fans, everything else you hear is from the computer itself. There's no other mechanical device involved. Dick Jensen was another one who rocked up. He did weather forecasting, and programs were of a kind that needed a loudspeaker, and he could tell if something went wrong instantly.
People were gradually saying, well, we need to stay on. We need more work done. And they said, well, we don't have any staff.
Typical staff might be around about 10, I suppose. You needed one operator, preferably two, of course, because you'd need a lunch break or a morning tea break or something like that. Be the head, secretaries and typists and things like that, and people to punch cards for you. Basically, you needed 2 engineers, but there were more than that much of the time. In terms of females, there are at least 5. Margaret Oates, the first main programmer, who was employed even before UTECOM arrived, she was there. There was Gay Ellis, Jean Robb, programmer, and this other lass whose name escapes me just at the moment. It was a sizable team in a very small space.
The original DEUCE computer from English Electric had been used for designing the Canberra bomber.
The legacy of UTECOM has got to be the invention of George, the zero address language of Charles Hamblin.
For the first couple of years, it was used from when the engineers turned it on every morning at 7 a.m, probably until about 8 o'clock, 9 o'clock at night.
The Anderson analysis program, which was a regular job run every Thursday night, was the listening cabinets or the viewing habits of TV and radio listeners in the whole of Australia. I would say it was among the first, if not the first, because the data would come in on punch cards.
We had a lot of people interested in crystallography and other related nuclear, molecular subjects that were anxious to get ahead as well.
I spent some time in Sydney to develop a numerical weather forecasting program called the Equivalent Barotropic Model.
And there was a lot of life left in UTECOM after we'd finished, but they closed it down and scrapped it.
I was quickly taken up to the IBM mainframe in the other building. The moment UTECOM was turned off, the ley lines were drained of their mercury and the mercury sold. Murray Allen, the professor, sent the drum over to what is today the Computer History Museum. All the rest of the equipment was a sim scrap metal job, best I know.